the wave equation is based off of acceleration with respect to space and in respect to time. So originally we saw it like this, but it looks really confusing if you've never seen multiple variable math classes before, so we're going to change this up a little bit. Okay, so this looks a lot more digestible now. You just have one variable on the top and bottom. I switched out the fancy Greek symbol for a y and then kept the t and then put this x squared on the bottom. This whole thing means the same thing, just with one dimension instead of the triangle thingy meaning multiple dimensions. So these 2's on here basically means the second derivative of both things with respect to t and x, but what does that really mean? I don't know. It doesn't really matter. We're going to focus on this guy for right now. So the second derivative really represents like a curvature. It means when you have a curve that's going like this, it turns out to be negative. And if you have a smiley face, it's positive. So if it's curving up, it's positive. If it's curving down, it's negative. It doesn't matter if it's going like this. It's still going to be negative since it's looking like a frowny face. So now, what if we have a curve that looks like this? Well, let's find the points where it's not accelerating nor decelerating. If you're playing a game like Jetpack Joyride, you would flip upside down. Imagine sort of like that. Point right there and a point right there. See, right here it's curving down. That's like a negative. This is like a positive curving up. Another negative. Another positive. And later on, what we're going to be able to do is take this and then pretend like it's a rubber band and attach it to 2 walls and then model this rubber band and see how it behaves over time. So if you've ever taken physics or gone outside, if you throw a ball on Earth, say its curve looks like this. Say you go to the moon, you throw the same ball, same speed, it'll probably look like this. It'll just go woo. Because the gravity on the moon is a lot less than the gravity on the Earth. They're both negative right here, right? So this frowny face is a lot more frowny than this face of a frown. This curvature is a lot more than this curvature. It's not really actually the curvature. So the moon's gravity is like a lot less little tiny arrows at every single point, but the gravity on Earth has a much bigger arrows at every single point. Okay, so now we're going to forget about this fancy notation for right now. Let's say our acceleration is equal to 5. Okay, what does acceleration do? Acceleration changes velocity. Let's say we're at a point and we're going to go to the right. We're going to start at 0 miles per hour. Now after 1 second, we're going to be going 5 faster than we were going last time. Now right here, we're going to be going 5 miles per hour. At 2 seconds, we're going to be going 10 miles per hour. It's going to go faster and faster and faster. So basically, acceleration changes our speed. And now the same thing with speed changes our position. If we're at position 0 right here, let's say our velocity is equal to 5 miles per hour. So after 1 hour traveling 5 miles per hour, we go 5 miles. But let's say that our acceleration is 5 again, but we have an initial velocity of also, let's say 10. So let's say I can write it down in this equation. V is equal to VI plus our acceleration times our delta time. 10 plus acceleration of 5 times, let's say 1 second, that's equal to 15. Bang, bang, right there, same thing. Now if you've ever taken algebra 1, you learn this equation y equals mx plus b. This is the same equation of an integral, but just in really simple terms. You start at b, this is the same thing as saying b plus m, and then this is times our x right here. We just do this by whatever increment of time we want. Basically, we're not going to be doing a straight line. Okay, don't worry, this is all going to pull together at the end really easily. Now the left side of the equation, it kind of looks like, and again, remember these 2's mean acceleration. The difference between these 2 is this one's respect to x. So it's like if we have x over here and then this is y. Now this one is negative, but this doesn't have a t. Where's a t at? There's no t in this picture. So you have to use this one with a different graph. It looks like this. Now this is a negative second derivative of y with respect to t. And these are 2 separate things. You have to do them separately. But we already kind of talked about this one. But now we're going to be using the same concepts to explain this guy, but replace this whole thing with something better. If you've ever taken a physics class, you know that there's an equation called Hooke's law, and it looks like F is equal to k times some distance. This represents a 0-dimensional point attached to a spring. Force on this particle going that way is equal to k times d, where k is just some value of the spring. So every spring, if you have like a really stiff spring, it's going to be like 20. But if it's like a rubber band, it's going to be like 0.1. Now let's do a little physics problem. Now we have 3 points. Say this distance and this distance are the same. So we're actually just not going to worry about these at all. Just pretend like they don't exist. We're just going to be doing the vertical height of these particles. But pretend these 2 lines represent springs. y0. This is our point of interest right here. And I'm just going to call it y1. y2. So this is like the heights of it. If you remember that graph before, this is like that. Okay, and like I said, these 2 x distances right here and here are both exactly the same, so this particle is not going to be pulled left or right anymore than the other way. This distance right here, y2 minus y0, and this distance from here to here is also equal to y1 minus y0. So if you remember that the force is equal to the k value, you can make k whatever we want, doesn't really matter, times a distance. So the force on y0 from y2 is equal to k times the difference in distances. This is d right here. But we also know there's another force on this side, so we're going to need to use Newton's second law sort of stuff. The sum of forces is equal to the first one, y2 minus y0. Okay, that's the first force acting on this particle, plus k times this distance right here, y1 minus y0. This is all the forces acting on this guy. The equation for force is equal to mass times acceleration. This is actually exactly how our code is going to look later on. Okay, now pretend like you didn't see any of that. So now let's say we have a point right here, and another point right here. So if you remember that y is equal to mx plus b, and then we replace this m with the velocity, b with the original point of y. So let's just call this y1, y0, y1, y2. y0 is equal to the velocity between the 2 points, which is the slope here, plus y1. So it's like saying a graph with a line between the 2 points, and the slope between here is equal to velocity. If this right here represents our dx, our delta x, this guy right here can go away and turn into dx. And let's just pretend like this is dx, and let's just forget about it for right now. So let's just say that the velocity is the difference in the 2 points. So velocity is equal to y0 minus y1, just the height difference. Slope with a run of 1 and a rise of, let's say, y0 minus y1 is equal to y0 minus y1 over 1. So who cares? Just forget about this 1, like it even exists. Let's say velocity 1 and velocity 2. Velocity 2 is equal to y2 minus y0. You have to do the second point minus the first point. That's how you do velocities. That's just the change in the positions, right? Acceleration is equal to the change of velocity. And that means the acceleration at point 0 is equal to v2 minus v1. The change in velocity is equal to the acceleration at this point right in the middle. Put these two things in right here and over here. Now, if this looks a little bit familiar, that's good, because this is actually basically the same thing we wrote earlier with the force of the spring on the point. So it's y2 plus y1 minus 2 y0s. y2 plus y1 minus 2y0. Okay, now we can see that this is the same as that. If we say that f is equal to m times a, we can do a is equal to minus 2y0. Remember, this a represents the acceleration of a point like this. Remember, this thing represents the curvature. If it goes down, it's negative, and if it goes up, it's positive. Downwards, if this curvature is negative, then this acceleration of the point will also be negative in the same direction of the curvature. So if it looks like this, then this whole part right here will evaluate to be positive. So that means the point right here will want to accelerate upwards. So now if we have our same weird looking shape like this attached to some wall, then we look at these points right here where the jetpack person flips upside down. So we can say that the curvature is like positive here, negative. If then the curvature is downwards, if it's negative, then the acceleration of every single point along this line will also be wanting to pull down. So then this whole entire wavy looking thing will want to oscillate. Now, the wave equation actually looks like this, where there's a c squared. We can replace that spatial second derivative with the weird y2 plus y1 stuff. This right here, acceleration, is just that. This whole thing right here is this curvature with respect to space. So wherever this value is to be positive, our acceleration will want to be positive as well, satisfying the same equation. So you can also say a little thing here. C squared is equal to k on m. So the speed of the wave kind of is sort of c is equal to square root of k on m. Not really, but like it kind of works if you have like a perfect wave and stuff, but that doesn't really matter. So stability of a differential equation model, which is what we're going to be making, kind of depends on how small our dt is going to be. Let's say we have a plane at 100 miles across the US. He's going from California to New York. Let's say that his position of y is equal to 100 plus whatever speed he's going to be going at. Let's say his speed is going to be 70 miles per hour. It's a weird plane. Let's say whenever we multiply this normally by dt, what does this delta time actually want to be? Now, if you keep on evaluating this over and over and over again, we want this dt to be like something like 0.001. He evaluates it, it's going to be y is equal to 100.07 plus 70 times another 0.001 seconds. And then the next time he evaluates his position, he's going to be at 100.14 plus 70 times another 0.001 seconds. But you see, this is taking a really long time. He's only going from 100 to 100.07 to 100.14. So this is going to take a really long time if he only evaluates his position every single 0.001 seconds. Now let's say they get lazy and only want to evaluate it once in every 10,000 seconds, which is like less than 3 hours. But now his new position is going to be y 17,000, which he probably just overshot New York. So that's just stability. You need to keep this thing really small.